Okay, here's what we are going to do together in this video. We are going to build a real coding agent from scratch in Python. If you caught my Harness Engineering Masterclass, that one was the theory, the concepts, the vocabulary, the why. This is the practical companion to that masterclass. We take those ideas and turn them into a working code, one primitive per chapter. Now, a quick framing before we build. This is educational. So the agent we build is small on purpose. Its whole job is to make each primitive concrete in the least code that still teaches the idea. So of course, we will not be building the next Claude Code or Codex. Instead, this is built so we actually understand what is going on. So here's the whole series in one line. An agent is a model plus a harness plus a UI. The model is a stateless reasoning engine behind one API call. The UI is just how a human reaches it. And everything that makes it feel like an agent lives in the middle, the harness. Now, before we write a line, here's where we are headed. By chapter 14, this is going to be a real coding agent. It holds a conversation, it runs behind an approval gate, it plans a task, it checks its own work, and traces every call. But here's the part that actually matters. We build the harness ourselves, every primitive, starting from an empty file. It stays small, a few thousand lines across 3 little packages. I wanted to quickly also show the GitHub repository. The link to this would be in the description. If you go to the commits, you will see that it goes from chapter 0 all the way to chapter 14, and it builds up onto each primitive one chapter at a time. So you can follow along. So 3 layers, UI on top, the model at the bottom, and the harness in between. And the harness is what we spend the whole video. The loop, the context, the tools, the sandbox, the memory, and so on. And so this is how the effort is going to go. The model is one call we swap in at the very end. The UI is going to be a very minimal CLI until the last chapter, and harness is the rest of the video. 15 chapters, 0 through 14. Each one adds exactly one primitive, like I showed in the GitHub repo, in its mature form. Model, then history, instructions, context, tools, and all the way up to observability. And then finally, a real UI. Every primitive from the masterclass once in code. And like I mentioned, you can follow along. The whole course ships as one repository of Git tags. It goes from chapter 0 to chapter 40, one per chapter. And check out any chapter and you get the exact runnable agent at that point in the build. The whole thing runs on UV, and 2 ways that you can actually interact with is one, UV run demo that plays the chapter's scripted demo that I wrote for testing purposes. And then you can also do UV run agent that drops you into the live REPL. The code on every slide is exactly what's at that particular tag during development. On the what change slides that I will have for each chapter, I won't go and read every line, but the diff is a real actual commit diff for that particular chapter. So you can pull up the tag from GitHub and read every delta that I skip. The whole point is to look at those diffs to see what was added for specifically that chapter and hence that primitive. Now, a few promises we make ourselves upfront because each one buys us something later. We put the model behind its own package. That's one of the 3 packages. So that adding a new provider is just dropping in a file. And you'll notice this is a very similar pattern to how a lot of the coding agents are actually built. So we are just borrowing from there. Pi is a good example of that. The UI lives in its own package too. So the core never has to know about a screen's existence. Similarly, we lean on OpenTelemetry instead of hand-rolled logger, which means that now the traces can go anywhere we want. Today, it is going to be our terminal UI, but tomorrow, if you want to use third-party OpenTelemetry compliant collector like Jaeger, you can use that. So we will end up with 3 packages: UI package, model package, and a harness package. 3 packages, and the arrows only point one way: UI to harness and harness to model. And here's the rhythm every chapter follows. We build the primitive, we break it to show why it's needed, we fix it, and we demo it against a real model. Every chapter is a Git tag. So the previous layer wasn't wrong, it just wasn't finished. So let's start at the very bottom with nothing but the model. Chapter 1, let's go find the first thing it can't do. And the very first thing missing is going to be history. An LLM API is stateless by nature. One request in, an answer out, nothing is carried between the calls. Every bit of statefulness we have felt from a chatbot was a harness feeding history back, not the model remembering. So here's the whole agent for now. When you check out Git to chapter 01, this is all you're going to get. An agent class with one send method, and the send is a single chat call with no message list at all. There is a small REPL, so you can keep typing, but every turn is an independent call. And that one call goes through a scene. That is a free chat function over a provider, be it LM Studio, Olama, or OpenRouter. For this recording, I'm using Gemma 4 26 billion A4B, served locally via LM Studio. And I'm pointing that agent to this LM Studio running Gemma 4 26 billion. And if you want to have a fake provider to run the test, we just swap the provider in one line in one variable. Okay, so let's see this in action. For now, you will see a recording, but you can try it out interactively from your terminal. So as you see, if we tell it that your name is Gemma, it'll return for that particular call acknowledging that. But with the very next call, there you go. And this is because LLM API is stateless. The model forgets everything the instant it answers. Carrying that history forward is the harness's job. And that is basically the next chapter. So if the last chapter, it forgets the instant it answered, chapter 2 is to fix that. And honestly, this is the single most important idea in the whole build. The model is stateless, so the harness keeps the conversation and replays it on every call. And so it's just a list. We gave agent a self.messages list, and every turn we append the user's message, then send the whole list and append the reply as well. In the diff, that's the 3 lines, the list and the init, the 2 appends. That's the whole difference between a model that forgets us the instant it answers and the one that feels like it remembers us. Every primitive from here, instructions, tools, memory, hangs off on this one list. So let's look at it in a demo. Again, a recorded one. Let's take the same example as chapter 1. 2 turns. I'll tell its name is Gemma, right? It acknowledges that particular one. And this time when I ask its name in turn 2, it remembers. Cool. Same stateless model, but now with the history living in the harness, we get a different behavior. It remembers now, but it still has no static personality. Every turn, it starts blank. That's what instructions fix. That's the next chapter. The chapter 3, instructions. As we saw, it remembers the conversation now, but it still behaves like a stranger every turn. So a system prompt fixes that. One message, the harness prepends on every turn. You set it once and it sticks. And real projects have a whole file of rules. So here's what we do. The harness auto-loads the agents.md from the working directory onto that system prompt. The same convention as codecs and Cloud Code. In code, we add one step in agents.py that folds 2 things into a single system message. In this case, the system text. One is our built-in prompt, which is self.system. And the second one, it's the agents.md. So a loader is in instruction.py and it reads the file. And if it's absent, it just does nothing. So the instructions are a layer, not a replacement. This chapter also lands a workspace. This is a directory the agent owns with every path confined to it. Though the write and edit tools that use it don't arrive until later chapters. So here's the demo. There's an agents.md at the root of the project that says you are Gemma. So if I ask the same name now, it answers Gemma. That means that we don't have to start each session telling who it is. But the path that we hand it is just a string of characters. Reading that file is what the next chapter, context delivery, will fix. Chapter 4. So it follows our instructions now, but it only ever sees the text we hand it. So reading that file and getting the contents in front of the model, that's what Harness is going to do. So here's how we deliver it. We pick a symbol, say @ to tell the agent we are referring to a file. It can be any symbol. In this case, I've picked @, but it's our Harness. We get to decide. Then before the call, the harness will scan for any @path references. It'll read them off the disk and inject the contents ahead of our question. In code, that's just one loop in send. The for block in the deliver function. Notice the blocks are raw for now. It is reading the entire file and will handle capping that giant file so that it don't flood the window in some other chapter. Okay. So let's see it in action. So we have a facts.txt file with some movie trivia. The file says Ravina is Karishma and Karishma is Ravina. So I provide the file via @facts and then I ask who is Ravina and it answers Karishma. So it can now read a file. Great. All I had to do was reference it using @ symbol. And with @ symbol, it will know that it is a file. Look for that file with the path provided. In this case, facts.txt is in the root of the project. So it'll find it there, read it, and the entire content of that file was added to the context for the module. Now it can read a file, but can it act on it? And that is where tools come into picture. And that is our next chapter. Okay, we are at chapter 5. Look at how far we have come already. Our agent is able to hold a conversation. It is following our instructions that you provide either in the system prompt or in any of the file that you decide. I chose AGENTS.md so that it is compliant to the Linux Foundation. It can even read a file now by giving a symbol. In our case, it's @, but notice it is still only talking. It can tell us how to fix a bug. It can't fix it. Tools are what are going to change that. And with that, the model can finally act, run code, read and write files, search, and then keep going with the results. So what's a tool really? It's just a function plus a schema. That's it. We keep them in a registry in tools.py, and it hands the model the specs, then dispatches each call by name. And notice the split. The model decides what to call, but the harness decides how and then actually runs it. The loop itself is simple. Send with the tool specs, and if the model reaches for a tool, you run it, hand pack the results, and go again. But right now, our harness is capping it at 6 steps so that it doesn't spin forever. Then a couple of guardrails. File tools are scoped to a workspace that the agent owns. Scratch dir for now, so an experiment can't touch your real repository. And bash doesn't run on our shell. It runs in a sandbox the harness controls. Docker if it's there, or a local subprocess if not. And the dangerous stuff, ask for permission. So a tool like calculator that we build runs free, but bash and file writes will hit an approval gate. And if nobody's wired up to approve, it just fails and says no. So approval are scarce on purpose. This is what it would look like in code. In our run, we have specs that we get for each tool, and then this is the approval gate if the tool requires it. And then this is the registry that I was talking about. It's in the tool and tool registry. Sandbox command for when needed. Now, let's watch it actually do something. So I have a calculator tool that we'll be using for the demo forward. Now, in this one, I ask it for calculation and ask it to use the tool calculator. So instead of guessing, which is exactly what a bare model would do, it reaches for the calculator and comes back with the exact answer. And then I ask it to write a file, and there's our approval gate. It pauses, it asks, I say yes, and it writes it. That's the whole shape of it. The model asks, the harness decides, and the dangerous stuff waits for a human. But every one of those calls and results is landing in the same conversation right now. And that conversation has a limit. What we keep and what we cut is the next chapter, context management. So that is chapter 6. And this one is a direct consequence of the last one. The moment we handed it tools, everything started piling up into the conversation. Every tool call, every results, every file it reads. Histories get long and they get long fast. But the context window is finite. You let it grow unbounded and the model starts drifting on its own noise, repeating itself, losing the plot. So the harness picks up a new job that manages what actually fits into that window. And there are 4 moves for this, and it's worth having all 4 in our heads. Select, compress, write, and isolate. This is again from the masterclass video that we have done. Here, we build compress. When the history crosses a budget, we summarize the middle and protect the head and the tail, because models read the start and the end most reliably. And the whole trick is to make it shorter without losing the thread, the goal, the decisions, and the facts. The two moves here, and they live in compaction.py and limits.py. First, maybe compact. When we cross the token limit, it summarizes the middle into a single node and keeps the start and end. We'll see that in the next slide. And you can see here, we estimate the token first to see whether we should be compacting or not. And if we do need to, we will call the compact method. And then there is a clamp method, and we'll see that in the next slide as well. So in compact, as you can see, the very first thing we do is keep the head, keep the tail, and then for the rest, we just summarize it. And then for the second part in limits.py, we determine what is the maximum item characters that we want. And then we use that to clamp. And no matter the file size or the tool output size, we would clamp it to that much characters. Okay, so let's kind of prove this with a demo. I give it a tiny context this time around, right? And then I try to bury a code name under a bunch of turns of random chatter, enough to blow past the budget for that context. And watch what happens. You will see that it does the compaction. But when it does the compaction, it will keep the head and the tail. And there you go. Context compacted. It kept the start and the end. And now when we ask for the code name, hopefully it remembers that. Of course, it's going to remember this is a recorded demo. It's going to find out the code name is Crime Master Gogo. So the middle got compressed, but the thing that actually mattered survived. The window handled now. But notice it still works all of this from scratch every single time it runs. Giving it a memory is for the next chapter. Chapter 7, managing the window, keeps our agent sharp, but there's one loose scene left. It still rederives the same procedures every time. It has no memory of how we do things in this repository. That's what skills give it, an operational memory. Think of it this way. A tool is a verb, a skill is a procedure, how we cut a release in this repository, etc. And a skill is just a directory with a skill.md, name, description up top, and instructions below. So here's the trick, progressive disclosure. We advertise only the one-line description in the prompt. The full body stays on the disk until the model decides it's relevant, and then it reads it with the read file tool it already has. So we create a skills array, and then we add to our system prompt, the original one that had only 2, we add skills to it. So now at the start, we have 3 things that gets loaded automatically. One is the system prompt itself. The second is the agents.md that we already loaded in the early chapter. And now it will also load the skills, but not the entire skill, only the description and the name. And this is what the load skills looks like. As you notice, it returns only the skill name and description. And this is what parses the front matter that you would have in the skill.md file. Okay, now let's watch it load one on demand. I ask it to use the sign off skill. It reads the skill.md and replies in the end with a code word, Hyla. And that code word lives nowhere else. And that is the proof that it loaded the body itself, not from anything we had pre-injected. So our agent can now read the skill description and name. Based on that, it will determine whether it needs to load the entire skill when the user asks anything, and then it reads the entire body. And this basically example was just for that. Now, again, you can see what the sign off skill does in the Git repository. And just again, a reminder for each chapter, make sure you are checking out the agent at that very specific chapter. So in this case, you would have done git checkout ch07, and it'll put you exactly at the state when I ran this demo. Okay. So now it can load the skill and can do the procedural part. But what about running code that we don't fully trust on our own machine? We will handle that particular fix in the next chapter. Okay, so our agent runs code now and it follows procedures too. But here's the thing we have been quietly living with. All that code has been running on our own machine, and the model will happily ask to run anything. The prompt is intent, not containment. So the boundary has to live in the harness. And so the move is start closed, network none, we'll have file system scoped, credentials absent, and then we climb the ladder only as needed. chosen by the blast radius, of course, an OS sandbox, then containers, maybe a user space kernel, a micro VM, and the bash tool now runs inside the sandbox. That's the change we're going to make. So then we harden every seam the untrusted code touches. Read file that could reach our etc password. Now we can confine it to the workspace. The verifier that used to run the candidate code with our full environment, well, now we scrub it. And the rule underneath it all is don't tell the model not to touch secrets, just don't give it secrets. Okay, so let's look at some code changes that we made in this particular chapter. In code, we now have a small change in agents.py. We now start triggering compaction on the model's reported token count, not on the estimate. So you will see that the last tokens is now model reported usage. And that is what we'll use to determine whether we need to do a compaction or not. There's also a verification helper file that shows up here, but it's only exercised by the sandbox for now. The loop doesn't call it until the later chapter. Okay, but let's look at the sandbox part. That's what got a major upgrade. So now in sandbox.py, we have Docker with no network, a non-root user, its capabilities dropped, a read-only file system, and hard cap on the memory and processes. If the Docker isn't there, we fall back to a scrubbed local run. The read file also gets fenced to the workspace. So the model can't reach out and grab the etc password that it otherwise was able to. Let's watch the hold. I ask it to run a shell command. I approve it, and it runs inside the box, working directory /work. Then I ask it to read the etc password file with the read tool, and it can't. Path outside the workspace. There we go. So the boundary lives in the harness, not the prompt. Code runs safely now, but it all still lives inside one process. You kill the agent and the whole conversation is gone. That's where the next chapter, durable state and memory, comes into picture. The harness writes the session down to a disk as a JSONL file, one message per line in a new module called memory.py. We give the agent a session, it loads history on startup and saves after every turn. So you kill the process, restart, and we pick right up where we left off. Log isn't a memory until we can recall the right slice. So there is also an episodic search, which is a search memory tool that we add in this chapter. It's a plain keyword search across stored sessions. This is the save session, the load session, and then the search session. This is, like I mentioned, a plain keyword search across all stored sessions, no embeddings. If you notice, this is similar to what Hermes agent does. This is a borrowed concept from there. That's the select move applied to history. Okay, let's prove that it actually works. I tell it an amount, and then I kill the process. I start a fresh agent on the same session and ask what the amount was. And here we go. The fact outlived the process that held it. So that is what durable state provides us. In this case, it's a session file on the disk in a JSONL format. And in this particular case, you have the ability to create a new session and start that session. And as you notice, the agent now loads the session by default, a hard-coded name for now, but you can also pass in a parameter to load any specific session, and it will save the session after each turn. Our agent survives a restart now. It's a state that lives on the disk. But look at what a turn still is. It's one loop, one shot. A real task isn't that. A real task needs planning, act like I mentioned. And buried inside a single loop, we can't hook into those steps. We can't gate them and we can't see them. That's chapter 10. And here's the fix. We add a control plane, a new orchestrator module, which is the orchestrator.py here. The split is the whole idea. The model plans the steps as JSON and the harness drives them. Gate each step through an approve check, execute, retry on failure, etc. And notice the agent's loop doesn't change at all. Main just gates a /plan command that hands the task to the orchestrator. The agent still does the work. The harness owns the shape of the workflow around it. We add a plan, and then we add an approve inside the run itself. Okay, let's watch a demo then. I give it a small multi-step calculation with a /plan. It writes the plan out as steps And then the harness runs each one and shows the result underneath. There we go. You see the shape of the workflow, not one opaque turn, but different steps as per the plan executed in that order. But notice every one of those steps still shares the single context window. So a big job might pollute it when it runs many tools and other dead ends. So that's what we're going to fix using subagents in the next chapter. Chapter 11, subagents. A fresh agent for a self-contained subtask. Its own context, its own tool, run to completion, and we keep only the answer. In code, it's just one module, subagents.py. Run subagent builds a fresh agent and returns the reply, not the transcript. And it exposes two tools to the model, delegate for a single subtask and a fan out for a batch that runs in parallel. And that's the point. Context isolation is a feature. Okay, here's the demo. Two subtasks in parallel. I fan them out. One computes 12 squared and the other one is naming a primary color. Two clean answers come back, 144 and red, order preserved. And neither one saw the other's reasoning. That is what subagents provides us. So it can delegate now, but it still just tells us done. Did the work actually succeed? There's no proof. And that's what the next chapter will give us. In chapter 12, the agent does the real work, agent delegates now, but done is still a sentence, not a fact. A confident final sentence should not be taken as proof. We can build something in Harness that gives us the receipts or demands receipts. And here's the twist. It doesn't run the test itself. The model does with the bash tool or any other tool that it has access to. The harness just watches the transcript and it won't accept done until it sees a real passing run. And that might be an actual exit 0. How does it know what to run? It reads in our harness from agents.md a testing section that names the command to run. It can be npm test, it might be go test, it might be uv run verify, which is what I'm using. Whatever our repository uses, it can be language agnostic. And it only fires when it matters. The gate arms only when the turn wrote a code file, which is decided by the extension of the file. If a plain question is asked, there is no gate. And that's basically how it is doing it. So if you see here, this is the testing section of the agents.md. That's what it's relying on. That's what our harness right now is relying on to know what and how to run the test. And then this is where it checks whether the file that was changed or the file that was created is a code change or not. And based on that, it'll decide on whether to enforce that test command or not. Okay, here's the demo. This is pointed at this very repository, right? So I ask it to tidy a doc string in the harness file because it changed code. The harness won't take done until it runs the UV run verify and sees it passed. You'll watch the model run it and only the real green result is accepted there. The agent held to the same bar we hold ourselves. Next, we are going to tackle observability. So our agent verifies its own work now, but when a multi-step run breaks, the failure we see is almost never where the trouble started. The interesting bug usually is 3 tool calls earlier, right? And if all we printed was the final answer, we are driving blind. So we need to give agent a tracer. Tracer runs through the loop and records every step as it happens. Model calls, tool calls, even the verify and plan steps. We decide what we do with the tracer that we start. How long, how many tokens, what it cost, and for tools, the exact arguments that were passed in, the results that came out. We will also add a pricing table in the model package. So the cost comes from there. A local model is read as free, while the hosted one gets metered. And the shape of it is one emit can have many sinks. The core fires each span once, and through an event seams, it can be read by multiple consumers. It can be a UI panel, it can be a JSONL file, it can be a console printer, or it can be an OpenTelemetry compliant collector. So in code, here's the tracer. This is where we are recording the LLM. This is where we are recording the tool with all its arguments and all. And then in the events.py, you will see that these are all the OpenTelemetry GenAI seam. It has the GenAI dot operation, GenAI dot usage, etc. And then in the pricing.py, we do cost from usage. Now let's take a look at that demo. Here we are having one calculation that open up the trace. And you can see when you ask something that does a calculation, after the answer, um, you'll see a row of a model call with the cost. In this case, given that it's an open source model, you'll see it's 0. But now we can see inside every run. We see the LLM call, we see the tool call. In the tool call, we see what was the input. In this case, it was expression was 256 by 8, and the output was 32. And then there was another model call that used some time, some token, but the cost was free. And up until now, you have seen all of this through a REPL. That is the command prompt that we are running through. How do we now upgrade this with a real UI? That's what the last chapter is about. Here we are, chapter 14. Now that we can trace every call, we can plan, we can verify and remember, we watched it through the REPL. Now we want to complete those 3 packages. We saw the model package, we saw the harness package. Now we are going to look at the UI package. So the whole agent equals model plus harness plus UI comes the full circle. Time to give agent a face. So a real terminal UI. We run it with UV run TUI, and we get 2 panes, the conversation on the left, live trace tree on the right, the same spans from the observability chapter taking with tokens and cost. And this time, notice also the approval gate. It's now a model that shows a real unified diff for a file edit as well, not just a bash command. And here's the key point in code. The UI doesn't re-implement the agent. It runs the same agent in a worker thread and renders what the tracer records. And it works on a Git work tree of our repository, so our checkout stays untouched. And the UI package is the only one that imports texture. A good UI is a consumer of events, not an owner of them. Okay, so this one for the final demo is the same agent, finally visible, run with UV run TUI. I ask it to create a file, and then an approval gate shows up as a modal dialog box. There we go. I allow it. And on the right, the trace tree ticks up. Turn 1, the model call, the right, tokens and cost. And that's basically the finish line. Agent equals model plus harness plus UI. And we built the harness ourselves, every primitive from an empty file. So now let's recap what that adds up to. So zoom all the way out. That's the whole build, from an empty file to a working agent, 1 primitive at a time. 15 chapters, 1 primitive each. And here's the thing to sit with. The model barely changed. Well, actually, it did not change. Not the weights, but the harness is what turned that model into an agent. About 2,500 lines of Python running on a model on our own machine. Each chapter, again, is a Git tag. So you should be checking each chapter out, see what the agent at that particular instance looks like. All of the exercises that I did were done in a similar fashion, where I would check out the Git repository to that chapter and start the REPL using UV run agent. If you want to try out at the end of the chapter 14 with the terminal UI, all you have to do is check out main and do UV run TUI, and you will be put into the terminal UI itself. Again, do not expect a fully functional, very polished agent. This is an educational repository with the intent more on how each of these primitives work and how very little code can make a big difference to what we are trying to do. What I also want all of you to pay attention to is when you look at the coding agents, particularly the open source coding agents, look for these patterns. Look for how they are written, how they are architected. One of the architecture pattern you saw here is UI only talks to harness, harness only talks to the model. Hopefully this removes the curtain of magic from the agents that you are working with on a day-to-day basis. So do check it out, run it yourself, and hopefully this is helpful. Thank you.